We are going to introduce a number of concepts that form the basis of the current Polaris capabilities. We will talk about the visualization of the primary measures of effectiveness, the implementation of the A-star route choice model, and the details of the implementation of an en-route path choice model that can be dynamically called by traveler agents. In order to model the flow of traffic on the road network, Polaris uses a queue-based approach known as the Newell model. The solution of Newell's model accounts for several interesting operational characteristics. The backward wave propagation in queues is modeled, as well as the mechanics of merging and diverging highway sections. The flow through intersections uses a cellular flow approach and determines the vehicle transfer based on vehicle demand, link flow, and available link supply. Polaris accounts for the difference between arterial and highway facilities using different parameters for wave propagation and jam density. The Polaris implementation is capable of modeling both capacity and lane reductions. The Polaris implementation of Newell's model is capable of reproducing quite realistic traffic flows. The performance of the network can be examined using measures of effectiveness such as vehicle miles traveled, vehicle hours traveled, and link travel delays. The capacity constraints on turning flow is derived from the FHWA Highway Capacity Manual. The Polaris network model is being calibrated against the regional highway occupancy results provided by the Chicago Metropolitan Agency for Planning, CMAP. Polaris uses, of course, a fully developed agent-based architecture. This means that individual link agents compute the desired flow according to Newell's model. The results are then passed to individual travelers who ratify the suggestion and move themselves along the route. The approach is functionally equivalent to a non-agent-based approach, with the added capability of easily introducing heterogeneous agent behaviors. The Polaris interface can display several types of link measures of effectiveness, in short, MOEs. The first is the link travel time. Here the height and color of the bar indicates the current travel time of the link relative to its free flow travel time. The taller bars indicate longer than normal travel times. The next is the link speed. Similar to the link travel time, the height and color of the bar indicate the relative speed of the traffic flow on the link. Taller bars indicate slower than normal speeds. Finally, the link density. This plot shows how dense traffic is on a link at the moment. The taller bars mean that the link is densely packed. A graphical representation of link queue length may also be displayed. Several two-dimensional plots reveal meaningful information about the network model as a whole. First, we have the VMT, or vehicle miles traveled, as a function of time for the entire network. Next, VHT, or vehicle hours traveled. These three plots show cumulative arrival versus departures. The in-network plot shows the number of vehicles currently in the simulation. Finally, three plots show the average link travel time, link speed, and link density for the network as a whole. Plots are not limited to network-wide statistics. We will select an individual link and look at its MOEs over time. Let's take a closer look at the downtown. First, we can browse to find a link with interesting characteristics. This is the time it takes to transverse the link. This is the effective speed on the link. The link density represents the density of traffic on the link over time. A traveler's path choice in Polaris is computed on an individual basis. This fundamental routing approach uses an A-star shortest path algorithm. Travelers may route using delays derived from historical information or prevailing information. The algorithm is able to account for facility bias as well as perceived turning delays. The Polaris router is agent-based, like all the other components of the application. It supports multiple user classes, which will use different information sets in their routing decisions. The agent performs its own route choice, allowing each traveler to have their own custom routing routine, knowledge, and en-route preferences. Polaris supports en-route path choice. A traveler's decision to reroute is ultimately determined by a bounded rationality which evaluates the time they will save by switching against how close they already are to their destination. This evaluation may be motivated by several factors including excessive delay, their daily activity pattern being replanned, or adverse special network events such as weather or an accident. Using the selection feature, we can scan travelers and review individual paths chosen. This person utilizes a highway to get from their home in the suburbs to their workplace downtown. The selected vehicle is drawn a little bit larger and highlighted in pink. As we run this simulation, the vehicle can be seen moving along its path, while its attributes such as estimated time of arrival update second by second on the right-hand side. In this video, we can see that the downtown is experiencing heavy winter conditions, slowing traffic in the affected area. The vehicles colored in gray have opted to change their path en route. By selecting this vehicle and reorienting our view, it is possible to see the original path in gray versus the current path in blue. Notice how the vehicle sidesteps the adverse traffic conditions. This concludes this section on the current Polaris route choice model.